In this video, let us try to understand about clock uncertainty, and the command that we need to use is set clock uncertainty. So coming to clock uncertainty, set clock uncertainty command lets the user define the clock skew information. Basically, this is used to add a certain amount of margin to the clock, both for setup and hold times. During the pre-layout phase, one can add more margin as compared to the post-layout phase. Generally, there will be two stages, that is pre-layout and post-layout. So pre-layout is before PNR and post-layout is after the PNR, where we get the routed database. So in pre-layout phase, this uncertainty margin will be more, whereas in case of post-layout, it will be less. During pre-layout phase, this margin will be more, and during post-layout phase, this margin will be less, as I told you. So coming to ideal clocks, so ideal clock is something like there won't be any write transition and fall transition. So it will take zero time to rise from 0 to fall, means instantaneously it will rise from 0 to 1 and it will fall from 1 to 0. That is something which is called as ideal. If you want to know like what is meant by ideal clock and practical clock, I have made a video, please go and check that video. So for ideal clocks, clock edges are arrival times, but for real clocks there may be variations in arrival of clock edges. For example, consider a clock with 1 nanosecond time period for ideal clock. So you can see this particular example here. So this is an ideal clock. So here time period is 1 nanosecond. So these are rising edge. So black is something which is rising edge and green is something which is falling edge. So for example, consider a clock with 1 nanosecond time period. So here time period is 1 nanosecond. For ideal clocks, rise edge comes at 0 nanosecond. So rising edge is something which is coming at 0 nanosecond and falling edge is coming at 0.5. So this is falling edge which is coming at 0.5 and again rising edge is 1 nano. So rising is at 1 nanosecond. Whereas if you see for a real clock, there may be variations like rise edge comes at 0.02 nanosecond. So in ideal, it is coming at 0. Whereas in case of real clock, which is something practical, it is coming at 0.02 nanosecond. And falling edge is coming at 0.54 nanosecond. So this is falling edge, which is coming at 0.54. And again, rise edge is again coming at 1 nanosecond. So you can see the difference here because of this variation of this particular edge. Here the time period is 1 nanosecond, whereas here time period is 0.98 nanosecond, whereas this is causing an issue like time period is getting reduced. So you can see here set clock uncertainty for ideal clock, time period is 1 nanosecond, and because of some amount of uncertainty or some issues, there are variations because of which instead of 0, it is becoming 0.02 in case of practical clock, or else you can call it as real clock, whereas falling edge is coming at 0.54 and again rising at 1. So here because of which time period is getting reduced. Instead of 1 nanosecond, it is becoming 0.98. So let us see why these things happen. This happens because of clock skew, crosstalk and on-chip variation. Here OCV stands for on-chip variation. This will affect the timing. To model these variations, clock uncertainty constraint should be used. So ideal and practical will not be same. There may be some variations. Those variations are because of clock skew or crosstalk or on-chip variation. So these effects should be taken into consideration. It is strongly recommended that users specify a certain amount of margin both for pre-layout and post-layout phases. Generally for pre-layout phase, this margin will be more and for post-layout phase, it will be less. The main reason for doing this is to make the chip less susceptible to process variations that may occur during manufacturing. So in order to overcome this, we need to give some amount of margin, that is uncertainty. So you can see here there are two types. One is intra-clock, another one is inter-clock. So inter-clock means here two different clocks for two different flops. Whereas intra means only one clock for two flops. Remember this point. Intra means only one clock and the same clock is being applied to both launch as well as capture. Whereas inter means two different clocks, that is clock 1 and clock 2, that is applied to two different flops. So for launch flop, it is clock 1, for capture flop, it is clock 2. So understand this difference, intra and inter. Now coming to the syntax, according to design compiler, so set clock uncertainty. So these are the switches, hyphen, from, followed by you have to give the clock list. So this will specify inter clock uncertainty, that is source clock. Next, hyphen 2. It specifies inter clock uncertainty destination clock. Next, there will be something like rise from, fall from, rise to, fall to, rise from followed by clock list. So it specifies interclock uncertainty, that is source clock. So remember, if it is from, it will be source clock. If it is to, it will be destination clock. Next, hyphen rise. It specifies interclock uncertainty for rising clock edge, and hyphen fall will specify interclock uncertainty for falling clock edge. and hyphen setup and hyphen hold. Hyphen setup means specifies clock uncertainty for setup check, and hyphen hold will specify clock uncertainty for hold check. Next, followed by the uncertainty value and followed by the object list. So this is the syntax according to design compiler. Now this is the syntax according to Genus, which is from Cadence, whereas design compiler is from Synopsys. So set clock uncertainty hyphen from edge. So rise clock edge for from points, that is rise, fall or both. Next hyphen from source clock for interclock. So simply remember hyphen from means it will be source, whereas hyphen 2 means it will be destination clock. So please go through this particular slides, like most of the switches will be same. Next, this is the syntax according to the prime time, which is from Synopsys. So again, all the switches are same. So please go through this slide. For your understanding, I have included syntax from all the tools. So you can ignore these examples as of now. We'll see more examples in the upcoming slides. So this is the syntax according to the tempers. Same thing, set clock uncertainty. And switches are hyphen, fall, hold, rise, setup, and rise from, fall from, rise to, fall to. So most of the switches are same and the descriptions are given here. Please go through this slide as well. Ignore these examples. Once we see some of the examples in the coming slides, we'll come back to this. Now see, what is intra-clock and inter-clock? As I told you, intra means only one clock will be there, which is given to both launch as well as capture. Whereas inter means two different clocks, one is for launch, another is for capture. Uncertainty is classified into two types. That is intra-clock uncertainty and inter-clock uncertainty. Intra-clock uncertainty between two different clocks having same clock. So intra means two different clocks having same clock. Clock skew can be between different points of the same clock. Different points of the same clock. Next, inter-clock uncertainty. It is between two different clocks having two different clocks. So you can see here, two different clocks having two different clocks. That is clock 1 and clock 2. So clock skew can be between different clocks. So skew here will be between clock 1 and clock. So see this example. So here we are using a constraint called as set clock uncertainty hyphen setup. So hyphen setup is for this portion and hyphen hold is for this portion. As we already know, setup is something like what is meant by setup according to the definition. The minimum time for which data should be maintained constant before the arrival of clock is called as setup. So if you take this as the edge before the arrival of clock, here data will be maintained constant. Whereas hold means after the arrival of this particular edge, after this the data should be constant. So according to the definition, we know this is setup and hold. So uncertainty is something that is again same before this particular edge, and if it is after edge, it is called as hold uncertainty. So let us see this example. So here we are taking an example of intra-clock. So intra-clock means only one clock will be there, which is given to two different clocks. So I'm taking the same example, only one clock that is applied to two different clocks. So set clock uncertainty hyphen setup 0.5 and hyphen hold 0.25. Here remember this point, setup and hold values will not be same. Generally hold value will be less compared to setup. Why? Because in setup we are considering both skew as well as jitter, whereas in case of hold we will be considering only skew. Why we are not considering jitter is because here launch edge and capture edge will be same while doing hold check, whereas it will be different edges in case of setup. And again this point is valid only if there is one clock which is given to two different clocks. Suppose if there are multiple clocks like fast flow and flow fast, again the scenario will be different. So that one we'll see in the next video. So see here, hyphen setup is 0.5 and hyphen hold is 0.25, and where we are applying this is get clock CLK. So for this particular clock, uncertainty is 0.5. So before this uncertainty is 0.5 and after this clock edge uncertainty is 0.25. So before this is for setup, after this is for hold. So the same thing I have indicated it in the form of waveform. Now see the next example. Here also we are considering intra-clock. That is same clock we are applying to two different clocks is called as intra-clock. So set clock uncertainty 0.5, get clock CLK. So here we are not giving either setup or hold, means it is applicable for both setup as well as hold. Means setup uncertainty is 0.5 as well as hold uncertainty is also 0. So this is another example. Coming to next example, again we are considering intra-clock. Intra means one clock applying to two different clocks. So set clock uncertainty hyphen setup 0.5 and it is at get port CLK. So here we are giving only setup uncertainty but not hold. So for this particular thing, we need to consider only setup uncertainty of 0.5. Coming to next example, again we are taking intra-clock, means one clock applied to two different clocks. Now here, according to the constraint, we are taking only hold uncertainty. So hold uncertainty is 0.2. Set clock uncertainty hyphen hold 0.2 get clocks CLK. So simply remember this point. If you are giving only hold, it is hold. If it is only setup, it will be setup. Suppose if you are not giving either setup or hold, then that value will be both for setup as well as hold. Let us see one more example. This is related to inter-clock uncertainty. So inter-clock means two different clocks which will be applied to two different clocks. Here clock 1 is applied to launch clock and clock 2 is applied to the capture clock. So the constraint here is set clock uncertainty hyphen from clock 1 to clock 2 and hyphen setup. So here we are going to the uncertainty value of 0.6. Now let us see how the waveform looks like. So here, if you observe here, we are taking two different clocks. So I'll be explaining you the three cases. Like when there is no skew between clock 1 and clock 2, that is, we will see the case of zero skew. One more thing is positive skew and one more thing is negative skew. So let us see zero skew. So here there is no skew difference. I mean starting points are same. And here according to the constraint, setup uncertainty value is 0.6. So make sure like this uncertainty will be checked at the capture clock. So here this uncertainty value is 0.6. You can see this figure in case of zero skew. So for zero skew it looks something like this. Now let us see about positive skew. So positive skew means the clock 2 is pushed towards right hand side. So generally this positive skew is good for setup and it is bad for hold. I'll explain you about all those concepts in detail in the upcoming videos. So just now according to the constraint point of view, look this particular waveform. So this is positive skew whereas setup uncertainty value is 0.6. So waveform looks like this. If it is negative skew, thus clock 2 is pushed towards the left hand side. So here the starting point is here, whereas here clock 1 is at this point and the value is again 0.6. So the waveform looks something like this. So see it clearly. So this is zero skew, this is positive skew and this is negative skew. One more example regarding interclock. So as I already told you, two different clocks will be applied to two different clocks. Here I am going for hyphen hold. So here only hold uncertainty will be there. That is 0.9. So again here we are seeing three cases. So according to the waveform, we shall see if it is zero skew, how the waveform looks like. If it is positive skew as well as negative skew. So for zero skew, the waveform looks something like this. And here I have indicated the hold uncertainty value of 0.6. So already we know the definition of setup and hold. So for setup, the minimum time for which data should be maintained constant before the arrival of clock. Suppose the clock is getting triggered at this point. So till some point data should be maintained constant. If it is hold after the triggering of clock, data should be maintained constant. So now here we are taking hold uncertainty of 0.9 and this is the waveform for zero skew. Suppose if it is positive skew, simply this clock 2 will be pushed towards right hand side. So it will look something like this. If it is negative skew, it will be pushed towards left hand side. So it will look something like this. Next, intra-clock. So here set clock uncertainty hyphen setup. Setup uncertainty is 0.01 and it is get clock CLK config. If it is hold, it is 0.002. As it is intra, only one clock will be there that will be applied to two different clocks. So here that name is clock underscore config. So this is setup uncertainty which is 0.01 and this is hold uncertainty which is 0.002. One more example for interclock uncertainty. So two different clocks are there and we are applying two different clocks. So first one is this clock and this is CFG clock and this is the constraint set clock uncertainty hyphen from this clock to CFG clock. Here hold value is 0.05 whereas setup is 0.1. Now let us see the waveform in terms of zero skew, positive skew and negative skew. So zero skew means there won't be any skew difference between the first clock waveform and second one. And these are the uncertainty value. So setup is 0.1 and hold is 0.05. I have indicated it. Please check this waveform. Suppose if it is positive skew, the CFG clock will be pushed towards right hand side. And again, I am indicating the value of setup as well as hold here. So this is the waveform. If it is negative skew, it will be pushed towards left hand side and this is the waveform. Here I am taking the clock frequency as same, but I am considering the skew. If you want, you can vary the frequencies and check like slow, fast as well as fast. So thank you. We have explored all the different cases in set clock uncertainty.